3D.2, and if you've noticed, maybe you've noticed, that every question that we're going to go through today is actually every question in the textbook, okay? Because it's useful to go through them and really take this concept, because this is really going to test you, okay? We are just bringing everything together, so we're going to go through it slowly, and then what I've pulled together for you is a booklet, okay? And this is past exam questions, because like I've said, we can anticipate there's going to be a first principles problem, we can anticipate there's going to be a conjecture problem, and we can anticipate quite readily, okay, that there's sort of been one of these, or one at least every 2 years, of these graphing relationships questions. Okay, so I've consolidated a number of past exam questions into this booklet. So we're going to do all of the textbook questions today, and then you have an opportunity to work on some of this booklet. Okay, not all of the questions we can do yet. I'll point out which ones we can as we get into it. So it says, here's f of x. Draw a graph of f dash of x and f dash dash of x. Now, it's pretty important that you pay close attention to that green table, okay, because that's a summary of everything that we've talked about, okay, those relationships between f of x, f dash of x, and f dash dash of x. So I'll give you maybe 30 seconds, just have a quick look at that. Because that's what we're going to be applying here. So looking at that, hopefully there's nothing outrageous that you're like, oof, haven't seen that before. Perhaps the last dot point, okay, the very last one down the bottom, and that'll come up in some of our examples. Okay, so let's get into it. So here we can see we've got f of x, it's a quadratic, okay? We can see it's got that parabolic shape. So you can know if we're going to differentiate it, it's going to be the equation of a line. All right, and then if we differentiate, then it's just going to be a horizontal line. So there's some things we can begin to think about, but we're asked to draw the graph of f dash of x. So the way we're going to do that is we're going to draw the sign diagram of f dash of x first. Because the sign diagram of f dash of x is quite easy to draw. F dash of x is just going to be positive when f of x is increasing, and it's going to be negative when f of x is decreasing. So what we can see is we have a stationary point here, we have a local minimum here, okay? So turning points on f of x are going to be the roots on f dash of x. So the coordinates of this point here are going to be exactly halfway between, so let's assume that's 1. We're safe to assume that. And we can see it is decreasing until we get to 1, so it's negative, has negative slope, and then it is increasing after 1. So remember this relationship, right? Like f dash of x tells us when f of x is decreasing and when it's increasing, and when it has local max and when it has local min. If we're looking at f dash of x, okay, if we're looking at this sign diagram, ignore that for now. This sign diagram would tell you there is a local minimum at x is 1, because it's decreasing and then increasing. Oh look, there's a local minimum at x is 1, okay? So then we need to draw a graph, okay, of a function with this sign diagram. So let's try and blot that out for now and just focus on this sign diagram. If we had to draw a graph, all right, that's, I'll just move the y-axis over a little bit. That's the x-intercept, okay? So that's going to be where it crosses the x-axis. And it goes from negative to positive. That means it starts down here and moves up there, okay? That this sign diagram, if you started with this graph and you were asked to draw a sign diagram, that's what you would generate. We're just doing the reverse. We're starting with the sign diagram and saying, well, that's its root, it's below the x-axis to the left of that point, and then it's above the x-axis to the right of that point. Okay? So that's how we draw the sign diagram, and then we can draw the corresponding graph. And look at that. We've got quadratic, okay? If you differentiate some quadratic, you're going to get some equation of a line. Okay, now let's draw the sign diagram of f dash dash of x. There are 2 ways we can do this. There's 2 points of reference I'm going to bring to your attention here. The first is that the sign diagram of f dash dash of x just tells you when it's concave up and when it's concave down. So we're looking along this function and we're saying there's no points of inflection. Nowhere does it change from being concave up to concave down. It is concave up for every value of x. So because it's concave up for the whole thing, there's no roots on our second derivative. It's just going to be a big positive. All right? It is positive because it's concave up for all values of x. And so if you were to draw a graph of a function that's just completely positive, all right, here's the x-axis, here's the y-axis, it's just going to be a line like this. Okay, so let me explain. Like, this is a quadratic, it's y equals x squared, of the form y equals x squared. So if we differentiate that, we're going to get dy on dx is 2x. And if we differentiate that, we're going to get d squared y on dx squared is 2. And that's this function here. This is the equation y equals 2. It doesn't matter what the x value is, the y value across this whole line would be y equals 2. Of that form anyway. So that's the first way that we can just say concave up, therefore always positive. Alright? This is the other way, is that we can ignore what's above and just look at this function. Because we're drawing the graph of the derivative of this function. Alright? The second derivative is just the derivative of the first derivative. So we're looking at that and we're asking this question, when does it change from increasing to decreasing? So you're looking along here, it's just always increasing. So that means the sign diagram of the derivative of this function is just always going to be positive because the slope is always positive. And so, same thing. Okay, so those connections, they're manifest everywhere. Let's have a look at this one. It's going to be a little bit more challenging. Some sort of cubic. Okay, I know that because there's 3 roots, 1, 2, 3. That's where it's crossing the x-axis. And so we're going to start by drawing the sign diagram of f dash of x. Okay, so that we're saying when's it increasing, when's it decreasing. So we can see we've got a local max here and a local min here, and we'll just approximate their values. We'll say -1 and 1. And so what we can see is it's increasing until we get to -1, and then decreasing until we get to +1, and then increasing again. Okay, this makes a lot of sense. I've said we've got some function up here, that's x to the 3 of the variety, x to the 3. So the derivative is going to be some function of x squared, so it's going to be a quadratic, and it's got those roots. So if we're drawing a graph of that function, all right, its roots are at -1 and 1, and it is above the x-axis, below the x-axis, and then above the x-axis again. Okay, let's do f dash of, so let's label them, that's f dash of x is f dash dash of x. Let's do the sign diagram of f dash dash of x. So let's do it both ways again. Look at the original function. Now remember, when we're talking about the second derivative, we're saying when is it concave up, when is it concave down, when's the point of inflection? Okay, so point of inflection is here. All right, or thereabouts at 0. It changes from being concave down to concave up. All right, so we'll put our 0 there. It is concave down and then concave up. All right, we can see concave down, concave up. That's the point of transition. And so we're going to graph this. So if we graph that, that's just, again, the equation of a line going through 0. It goes from negative to positive. Okay, so that's the first way we can do it. We can look at the function and go, well, when's it concave up, when's it concave down? The second way is to say, ignore that and say, if we're going to graph the derivative of this function, okay, we're saying, look, it is decreasing until we get to 0, and then increasing. That's mirrored on our sine diagram here. It's decreasing until we get to 0, and then increasing. And then we're just graphing the line from there. Okay, one last connection, and this is the very last dot point there. This is a point of inflection. The point of inflections on f of x correspond with turning points. That's a local minimum. Remember, turning points are local min or local max. So point of inflection on f of x is a turning point on f dash of x is the root. Root on f dash dash of x. You reckon someone's trying to break into the gym? Okay, so we'll move on to the next one. Are there any questions about that? Okay, so I'll still emphasise this. This is a pretty similar example here. We can see, we're going to draw the sine diagram of f dash of x. I'll start to move a bit quicker, I think, because we're starting to see the relationships a bit. And we're saying, when is it increasing, when is it decreasing? So we're looking at this function, we can see it's increasing until we get to 1. Now, I'm trying to draw the sine diagram to correspond with the graph in front of it. So we're increasing, so we have positive slope until 1, then we're decreasing until we get to 3, and then we're increasing. Okay, and again, think about it like this. If we were just looking at the sine diagram, it's going to say local max at 1, local min at 3, increasing, decreasing at 1, decreasing, increasing at local max, local min. Okay, again, this is a cubic. Okay, we have a single root here and a double root there. Whenever something touches, it's a squared root. We learned that in year 11. So let's go ahead and draw the graph of the derivative. So we've got 1 and 3, and it is above. Oh, come on, put a line them up here. Just try to line them up. So there. Is above, below, above. So that's f dash of x for us. This is 1, this is 3. This is exactly halfway in between 1 and 3. The vertex of the quadratic is halfway between its two roots. So that'll have an x value of 2. Okay, let's have a look at the second derivative. So now, I've already pointed out those two ways of doing it. Let's do it the second way this time. Okay, so rather than looking at the first one and saying when's it concave up, when's it concave down, we'll confirm that after. Let's look at f dash of x, because we know the second derivative is just the derivative of this one. And so we just ask ourselves the same question. When's it decreasing, when's it increasing? It is decreasing until 2, and then increasing after 2. All right, this function here is decreasing, and then increasing. So if we were to draw a graph of that one, Alright, so if we were to have done the first process I taught you, we're looking up here, we're saying when's it concave up, when's it concave down? Well, we can see concave down until this point, and then concave up. What's halfway between there? That's 2. So we can see it's concave down, f dash dash of x is negative, and then concave up. Okay, and again, let's emphasise that point. Point of inflection on f of x is a turning point. Okay, it's changed from increasing to decreasing on f dash of x, which is a root on f dash dash of x. Okay. All right, D. Let's draw a sine diagram. Okay. So you're just asking yourself, when's it increasing, when's it decreasing? So we're decreasing until 0, isn't it? That's a local min. Is it 0 in your book? Can I draw that up properly? Yes. 0, and then we're increasing until we get to 2, and then we're decreasing until we get to 3, we can anticipate that's 3. And then we're increasing. So increasing, decreasing, that's decreasing, and that's increasing. Fair bit going on there. All right, but if you're to draw the graph of this function, remember, we'll line it up again. Remember, you're just drawing when it's above the x-axis and when it's below. So we've got 0, 2, and 3. And we've got below the x-axis, so I'm just going to draw like that, and then it's above the x-axis like that, and then it's below, and then it's above. So it's doing something like that. Alright, let's draw the sine diagram of f dash dash of x. Okay, so we could use, again, either of those two processes. Let's look at the original function and spot the points of inflection. Okay, because that's a bit of a skill, I think. The increasing, decreasing, that should be reasonably okay. So we can see it's sort of concave up until this point here. That's all, that shape there is all concave up, and then concave down over that region, and then concave up over that region. All right, so this and this are our points of inflection. So the first one is going to be at 1, and the second one is between 2 and 3, 2.5. All right, and we've got concave up, so positive, concave down over that region, between 1 and 2.5, so negative, and then concave up after 2.1. All right, and then the graph of that is the y-axis, 1, 2.5, and it's above, below, above. Okay, look at that relationship again. Point of inflection, local max, okay, so point of inflection, turning point, root. Here, point of inflection, turning point, root. Okay, so I can emphasise that again. It's a great question to demonstrate. All right, I'm going to spin this one around. I've got 2 more. Okay, we sort of inverts our process a little bit. Now we're not. Let's read it. What does it say? It says start with, this is a graph. For each graph, this is f dash of x. Okay, this is f dash of x. Draw a graph of f of x. A possible graph. Okay, because there's lots of ways it could possibly be. Draw a possible graph of f of x. So, first what we're going to do is we're going to start by drawing the sine diagram of this function. Okay, we're going to draw a sine diagram of this function. Sine diagram is going to help us out a lot. Okay, so if you're in doubt, try to draw a sine diagram. Okay, of this function. And so that's just an indication of when it's above and when it's below. So we've got above the x-axis, below the x-axis, below the x-axis. Now remember, we're trying to draw a possible graph of f of x. So this sine diagram, this is the sine diagram of f dash of x. This tells us when, so let's write that, it tells us when f of x is increasing and decreasing. All right, that's what this tells us, okay? It tells us, what's that point there? That's a local max. It tells us we have a local max at -3. All right, and then it says, then it's decreasing. And what's going on here? This is a special case. What's that called? When it decreases, goes horizontal, and then keeps decreasing. So it's not a maximum, it's not a minimum. Stationary inflection. Okay, so we can see that from the sine diagram. F of x is going to have local max, okay, because we've got increasing, then decreasing. Local max at x is minus 3, and it's going to have stationary inflection at x is 1. Okay, we've got all the information to draw the possible graph. So, we don't know its x-intercepts. Okay, it could be completely above the x-axis, completely below. Alright, all we know is that somewhere there's a local max at x is minus 3, a local max there, and it is decreasing, it keeps decreasing until it gets to x is 1, in which case it goes horizontal and then keeps decreasing. Okay, so let's cover that a bit. Obviously bad scale. Alright, but what we've got, very tricky to see the link from this to this. Okay, easy to see the link from here to here. Okay, we can see increasing until we get to minus 3, then decreasing, gets to 1, still decreasing. Alright, goes horizontal, then keeps decreasing. One other way to check. Okay, here's f of x. Is this a suitable graph of f dash of x? Okay, here this would tell us, oh, we've got a local max there, all right, which means we need a root on f of x. Yep. Here this tells us we've got stationary inflection there. Well, a turning point. Okay, we've got a turning point because it corresponds with the root. Hit there. Okay, let's have a look at this one. Let's have a look at this one. So we've got f dash of x. Okay, this is the graph of f dash of x. We're just drawing a sine diagram. We've got minus 2 and 4, and we've got below, above, below. So what that means, let's use this sine diagram and let's list what it tells us about f of x. We're going to have f of x has local min at x is minus 2, and it has a local max at x is 4. Okay, decreasing till minus 2, then increasing, increasing till 4, and then decreasing. So let's put that on there. We've got local min at minus 2, so that's going to be here-ish. And then local max at 4, that's going to be here-ish. That's a max, so that means it's going back down after that. And y-axis is here somewhere. Okay, so there's one thing I've missed here is, do we know the point of inflection on f of x? Do we know the coordinates of that? No, I didn't cover it in this one either. So remember, this is the function f of x.
Can we put another derivative in the f dash of x and figure it out?
Yeah, that'd be one way to do it. That'd be longer. Let's try to just make the link without doing it. So what's the very last dot point say? It says point of inflection on f of x corresponds with turning point on f dash of x. Okay, so obviously there's a point of inflection here, all right, because we've got a local min and then we've got a local max. So somewhere in there, it changes from concave down to concave up. Other way, concave up to concave down. Somewhere in there. Where?
But what?
X is 1. Very good. Okay, so point of inflection, so we can shove that over. Okay, that's x is 1. Alright, point of inflection on f of x corresponds with turning point on f dash of x. Alright, So we can anticipate that point of inflection. And we can do so over here as well. We've got that point of inflection. Okay, that one's already given to us. But we have another point of inflection here somewhere, all right, where it changes from being concave down to concave up. All right, this is the tricky part. Concave down to concave up. Somewhere in between -3 and 1. Now remember, point of inflection on f of x corresponds with turning point on f dash of x. So that point of inflection corresponds with that turning point, that local max. So this point of inflection is going to correspond with this turning point. Are we given an x value for it, or? No, so we'll just say it's about -2, I think. So the point of inflection there is at -2. That's -2. Alright, so look, it's still got maintaining the same shape. Just making one more link for you between point of inflection on f of x corresponds with turning point on f dash of x. Alright. Now if you were to look at this, okay, so it doesn't say to do this in the question, but if you were to look at this, you could easily draw the graph of the second derivative. Okay, because if this is the first derivative, then the graph of the second derivative just says, when is this one increasing and decreasing? Well, you can see it decreasing until this value, increasing, and then decreasing. Alright, that's enough. Let's get out these booklets, let's give it a crack. Oh, look at that, there's actually a couple of examples in the booklet.